All of our three sessions this afternoon require extensive network applications and place demands on the network behind them. And they're really presenting the benefits and uses of the network. Our first speaker is Ted Hans, who's worked in the medical school in the University of Michigan and was, before that, heavily involved, and probably still is heavily involved in Internet 2. And if Ted can find the... Sorry, Ted. Right, so... Ted.
All set. Thank you, Michael. As Michael said, I'm Ted Hans from the University of Michigan Medical School, and I am talking today about new medical applications, or a survey of what I've learned in the last 18 months after leaving the national networking organization, Internet 2, where I was for 8 years. I returned back to campus, and it's interesting to see things from the end user perspective again after having spent so much time on national and international networking. And so I'm sharing this presentation in part for an exchange of information, to find others who are working in similar or complementary areas, and maybe sparking some information exchange or potentially some future collaborations. So the University of Michigan is a large public research university. The medical school is a pretty good size, certainly nowhere near one of the largest in the U.S., but we're attached to a very large hospital. So we have 2,000 faculty members in the school, and the budget is nearly $1 billion US per year. And what I was hired to do was come in and be an innovation manager for the medical school. That is, we have had efforts in terms of administrative computing, but no one's looked at how the medical school can be a real innovative leader in using information and communication technologies for teaching, learning, and research. And that was the perspective I came into this role 18 months ago. So a number of reasons why talk about this in an international context. That is, the University of Michigan really thinks about itself as being a global medical school. We have students who will end up practicing around the world. They'll be working with colleagues from around the world. And so it's important to think about medical school not just as an entity within a single city, but as truly in a global context. And again, with the networks that we've built, we really can virtualize the experience across whether it's education, clinical trials, or basic science research. And I'll give some examples that touch on those areas. So, very simple. You start off with things like image sharing. And we learned that the kind of images that you might use will get more and more complex, will drive higher and higher bandwidth requirements of the network. So one of the questions I might get asked is, what is the network requirement for these images? And the answer is it just increases continuously each year as you look at both multidimensional and higher resolution data sets. But we do have applications, for example, this is a picture I took of a medical school in China, where looking at images that we may be interested in because there are gastric cancers, for example, they occur much more highly in Asia than they do in the U.S., but with travel and other kinds of movement of people around the world, we may be exposed to those patients. So how do we actually educate our students about that? Well, one way is by having a partnership with this medical school in China where we share interesting cases with each other. Now, we can talk about moving the images around, but also could talk about actually sharing the instruments themselves, both for remote observation, but also for remote control, for operating the instrument. And so you have examples of electron microscopes, light microscopes that are used in a network basis because sometimes it's a rare device. So the world's largest high-voltage electron microscope in Japan is being operated by a researcher in California without him having to travel to that site. Then you might have light microscopes that may be located in another part of a campus where the faculty member in his or her office can be looking at it and operating the stage remotely, sort of more economical use of those devices, and bringing those into the network as just regularly available resources. Now, in these last two contexts, we're talking about just sort of moving information around. But the environment that I'm trying to build is one of a truly rich collaboration environment where you think about all four quadrants of time and place, where you have same time and same place, those of us interacting here in the room and the coffee breaks. Then you have different place at the same time, so you have the people who may be watching the netcast of this, but they're in a different location. Unfortunately, they can't participate in the coffee breaks, and so they miss out on some elements of the meeting. Then you have same place at different time, so that if I actually had written some notes on the wall, come back later and look at the board and see what was recorded here. And then different place, different time is somewhere someone else goes and looks at the recording of the netcast from this session. Well, the objective I'm working on is how do we make each of those four quadrants as functionally equivalent as each other, so that you really can not lose out in terms of collaborating with other individuals regardless of where you are and what time it is. So an example of a project that's just started extending into Europe started with that researcher I showed you at the University of California, San Diego, accessing the high voltage electron microscope. He started this program called the Biomedical Informatics Research Network, and these are neuroscientists who are working together to share information among their various projects. Right now, as I say, it started off in the U.S. with 26 sites across the United States, and they just added 2 sites in the UK. But they're working on creating these data sets of neurological images and mapping that to various ways of mining and exploring that information, regardless of where it is across the network. Some of the interesting things about this is, one is the physical infrastructure, the technology infrastructure to make this happen, the servers at each of the sites, the collaboration technology, but probably an equivalent, if not higher amount of work went initially into sharing the intellectual property rights, coming up with data sharing standards for the sites so they can move the information around each other. So when I look at lessons out there, it's not just about what model of a server did you use, but also how did you address these other policy and social aspects of communicating with the other groups. And so this is a very good example where they've explored all that in terms of both the policy side and the technology side. Now, one of the ways that we often communicate among these groups is using technology like the access grid for video conferencing. But you look at it from a medical context, one of the issues we have with this is that the limited resolution of each of these images. Because many things that we're looking at, whether it's we're looking at a scanned image from an MRI, for example, or something higher resolution, or actually looking, as an example I'll show later, at the hands of a surgeon operating within a patient, it's not captured within this quality video conferencing. So we started getting an understanding of how the access grid can build multi-site sort of persistent presence for collaboration. But what's really driving our interest is what's going on in the high-definition video space for video conferencing. So this is a project I participated in last year where it was led by the University of Washington, and the technology that John Delaney was showing at the last session is what we were using for connecting up to over about a dozen sites around the world. And so this was at a conference in Seattle last November, and they showed the different sites participating. A little close up you can see the multiple sites engaged, from 2 sites here in the U.S. This one right here, I'll show this image in just a moment in terms of high-resolution imagery. Another depiction, medical school, Ayan Baharan from SurfNet, and another illustration from connections from Australia and Japan. So in very high resolution, such that this picture here, Eric Hoffer at the University of Michigan is sitting in front of a large tile display, and with HD video conferencing, you have the ability to actually show the images in the background, very high resolution for teaching or shared research. Now, the stress this puts on the network, we're talking about 1.2 to 1.4 gigabits per second for each flow. So it puts a lot more stress on the network than the access grid. And so one of the things that I've been working on is bringing in a 10 gigabit per second circuit into my office to be able to start experimenting with these applications to find out is there validity in use and how we can apply them to medical education and research. Now, this connection that I'm getting right now is connecting to the ultralight physics network, because that's a group of people who've got similar interests in very large data sets and very large data flows. But if there are any people out there interested in looking at how medical applications can take advantage of optical networking, I'd be interested in talking to you. Because 2 of the examples that often referenced, One is high energy physics, and they're needing bulk data transfer, but that's not a real-time application. The medical applications are typically real-time. The other one is radio astronomy. That's a real-time application, but is generally very loss tolerant. If a radio telescope goes offline, you still have enough other inputs in order to correlate to create useful information. We are not loss tolerant with medical applications. So I'd be interested in actually looking at various medical applications that I'll show here in a moment, whether they can take advantage of some wavelength-based networking in order to provide the kind of quality service, security, and other attributes we need. So one of the big points for us is actually is training. As more and more of the surgeries either are bringing in new techniques or becoming much more specialized, the experts out there that we want to tap into may be spread anywhere in the world. And so a number of schools have been working together to provide mentorship opportunities across the network where you may be actually working with a surgical trainer that may be based on somewhere else across the network, and that may be a mentor situation where someone may be virtually looking over your shoulder, looking at your technique and advising you. And again, the inputs may be coming from completely different places than where you are located. And so one of the things that we've been working with Stanford is medical education of our students, where they're learning from experts like Leo Heinrichs here, who will be based at Stanford. Also in our own environment, we're starting to put together virtual reality and immersion environments around human anatomy. So this is an image of it's being displayed within our cave. And again, the idea is here, if we can network these environments together, we can have multiple students, multiple mentors working together and advising and consulting. So we're moving to the space where you offer an anatomy class, you want to use the best expert in the world for being a lecturer, and not necessarily who's willing to move to your city and teach at your university. So we've been testing this with Stanford, where, as I mentioned, lecturers from Stanford are teaching our students at the University of Michigan using 3D imagery that's projected, either projected or on a screen that they sit in front of, and they can interact with that lecturer as if a person was in the same room, pulling data sets across the network, and again, multiple students at multiple sites. Now, the thing that we learned a lot about is sort of, again, is the material useful in this context? Do the students learn? But we also learned a lot about the stress in the network. The faculty member who wanted to do this knew he couldn't run it in his office, but didn't know why. Well, the reason was it requires IP multicast, and he didn't know that. Our network, which is actually run by the hospital across even the research and education buildings, they did not support multicast because the same network that supplies all the health records for the patients and other production services. But it took me several months to bridge that gap between the faculty member who needed the multicast application and the production network people, to where today we actually do have plug-in any port and IP multicast is available. But it's that kind of glue. Again, when you're working from a national networking perspective, you don't always see it down to that level of a individual faculty member trying to do something that will have an impact on a larger organization. And we've also learned that even when it's plugged in and available, it doesn't mean it's always working correctly. This application requires a lot of context switching as you pass off to one individual or another individual's control of these data sets and communications that, again, flowing across multicast. And that changeover sometimes of tearing down and building up a new multicast group can take tens of seconds. And we've spent an awful lot of time debugging that network. And it seems, again, surprising that we're so many years into having multicast available, and it still doesn't work for application users. And that's one of the biggest cries out there, again, from the end user perspective, is we talk about these technologies, but really they don't work yet. And I'll tell you, multicast does not work yet for end users. And it couldn't be any more underscored until you actually try and use it in a production context. Now, some of the environments we're trying to build here are for research perspectives. There's a lot of work going on in terms of modeling, for example, physiological response. The number of universities have been involved in a project called the Virtual Soldier. And the idea here is actually to provide a tool in a handheld computer that a medic on the field would be able to diagnose the criticality of an injury of a soldier and make the decision, is this someone who has to be treated right away, treated before or after other injuries in the field here. And the modeling here is if a soldier was shot, how much time did you have actually before they could move to a critical phase of that injury. And these medics only have 6 weeks of training. So the point is you actually have to provide enough expertise in these models to actually to direct them how to act in the field. Well, to try and model the physiological response to a bullet shot takes a tremendous amount of work. And so we had to use a significant amount of supercomputing power to actually crunch and develop these models that are then used with various physiological inputs to direct them to make a particular diagnosis on an individual. Now, certainly we won't be to the point where we have supercomputers in the field, so we have to build a variety of models that are pre-established and then apply them, what we learn from them, to these handhelds out in the field. But we're using supercomputing in the healthcare field in a way that is quite advanced right now for the point of actually doing patient diagnosis. Now, the same modeling can be applied to a different context, and that is training individuals before they move into practice. So this whole area is emerging around what we call serious games, and it's one that's we have to be very careful about the word games because people might think that means it's frivolous or it's only for entertainment. But we're in the medical education field are looking at games that actually build on some of the infrastructure from the entertainment industry, but are now applying it to instructional contexts. And that is in both individual and multi-user contexts. How can you actually go through a simulation, which may be an individual procedure? How would you interact with a patient, or how would you actually do a particular kind of suture, for example, to multiple people working together, say duplicating the experience within an emergency room. So using, again, very robust models, using high-resolution networking to bring people together, and visualization to build this hybrid environment that allows you to actually make mistakes, and as many mistakes as you can possibly make until you get it right before you actually interact with your first patient. And I believe we all think that's a good idea in order to support the more expertise in these students. So mobile solutions, we talk about very high-end, these 1.2, 1.4 gigabit per second flows for HD video conferencing. Here with handheld computers, we're not talking about very high bandwidth, but more sort of ubiquity and also required sort of persistence of access. And we have everything going on in terms of students carrying around their lectures right now on iPods. The University of Michigan dental school and medical schools have been delivering the lectures through iTunes, so the students can download them right to their iPods and then re-listen to a lecture again while they're on their walk to school or on their jog. So it's changing how we deliver education out there to these students. But also we use it for things like tracking patient encounters. As a medical student, you have to see a certain number of patients, say pregnancies or heart attacks or strokes, and how you keep records of that. Keeping that all electronically means it always stays as bits and flows to the system, but it means there has to be ubiquitous connectivity wherever they may be, not just in our hospital, but in clinics and other remote sites. And you start thinking about an architecture that ties that all together. Then obvious things like delivering patient records, whether that's within the hospital or in the field with the medic. And then things like monitoring patients. One of the interesting things I've been looking at is how we're using things like wireless stents to track a patient who had a stent installed in a clogged artery. That we can actually, there's wireless devices being developed in the research labs now, such that stent can monitor the flow across it using a nanoscale device, so that you can just have a remote wireless monitor that's capturing information off that stent that's actually embedded within the person's chest, so they know if the flow starts getting constrained, it's time for the patient to come into the doctor, not just because it's been a week or 2 weeks or a month later, but because there's actually something that has to be responsive. Well, that kind of networking is, again, very interesting. How do you provide that kind of connectivity where the patient may be? Do you constrain them to his or her home? Do you allow them to have this connectivity at work? And what are the standards for doing this? Because, again, this is not very loss-tolerant applications. So we talk about this environment of all these pieces together, whether it's the servers, instruments, libraries of information, people, and so forth. How do we bring it together? Well, there's some interesting work around some advanced tile displays. So this is actually a part of one that was the University of California, San Diego showed off last September at 55 displays, all put together so you can actually look at a video conference of a person talking to you from a remote site, a high-resolution image of the data that you're looking at, that you can look at one level, and then you can zoom in at other level in the windows and compare that. But also you can have images that come from microscopy and from models that you've built. And it really is changing the experience. Instead of looking at it as one screen and flipping to another image, and flipping to another image, and flipping to another image, having this all available at very, very high resolution when you're talking about these high resolution displays and multiply it by 55 times. Again, significant amount of demand on the network because it's being remotely rendered, and you may be tapping into resources coming across far from the future. So the thing I'm looking at here is that we're looking at medical environment that spans across medical education, across basic science and clinical care, and needing to provide a common infrastructure across all of this so that the information that's developed in the basic science area does very quickly make itself to clinical care. So trying to build a common infrastructure across all of them. So at one point, talking about one network run by the hospital across our medical education and research facilities sounds like a liability because of issues around firewalls and whether multicast is turned on. There's a benefit in terms of maybe it may lead to quicker information flow across these various components of the spectrum. So again, going back to why I'm trying to bringing this to all of you is that when I was at Internet 2, I was the director of applications and looked across the entire spectrum of disciplines out there. Again, the kind of things that you heard John Delaney talk about, high energy physics, astronomy, and you name it. I thought the medical field was a place where some of the most innovative uses will come in the future, and where, in many cases, the resources are there to build this infrastructure. And I think that my experience over the last 18 months has really reinforced that as being true. And I really think this is an exciting area, but it's an area that actually, in many ways, is still way behind many other fields, and really needs some push to move forward. And one way to make that push is by those of us working together to help the physicians, help the researchers see what's possible. So we're really looking for opportunities where we can, think about global medical education, global healthcare environments, sharing experiences. As in particular, we have a much more global and mobile global community. And giving an example of what's going on within APAN, the Asia Pacific Advanced Network, has been doing a number of things in the medical space. There's a medical working group there that has been focused on using DVTS, or DV quality video conferencing, to show surgical training and education events. And at each meeting that they set the bar for a new kind of capability, bringing in a new country, bringing in a more higher quality experience, bringing in new people. And that's sort of a forcing function to get more and more cooperation among both the networks, the national networks that are supporting this, as well as the end users within the hospitals and schools who are participating. So one way to think about working in the future is by tying into these kind of collaborations or having duplicate experiences off on other national and continental networking activities. So as I said, throwing this out here because, as I say, looking at an environment that is, from an end user perspective, is not necessarily delivering the bandwidth that we need today. Things like multicast aren't working. That there's a clash between perspectives of firewalls from the clinical care, from the research side, and if you're building a collaboration, you have to consider both the policy side, like I said, intellectual property rights and data sharing standards, as well as the technical infrastructure for delivering that collaboration. So throw this out here as an opportunity for us to actually find other people with similar interests or supporting similar groups out there. Maybe it's just information exchange, pointing out opportunities, but maybe actually working together on some future experiments. So again, I appreciate the opportunity to come back wearing a different hat now and saying how we as end users really love all that you do with the national networks. But there's lots of opportunity, particularly in the healthcare space, to do some exciting applications that can really, again, show the future like John Delaney showed with his Neptune application. So thanks very much.
Okay, thanks very much. We have time for a couple of questions. Please.
Thank you. I was asking if you can think of any specific reason that will make you move away from multicast.
Whether we would want to move away from multicast? Yeah, so some of the solutions here are to try and fix multicast, make sure that everybody has, whether it's, moving to, away from the current models of multicast into the newer things in IGMP v3 and so forth. The other one is to move to application layer multicast and not have to worry about trying to debug the network and how the application works. And that's one of the hard things for the people who are the application users is that they can't make that decision. There needs to be more of a dialogue between the people who are building the application and the people who provide the network infrastructure. So there may be some solutions out there, but there's a disconnect between the application developers and the network engineers, and that's what needs to be closed.
Okay.
Do you want to look at the next slide? Yes, again, sorry.
No, no problem. Many of the applications you showed required video, and especially high-quality video. Do you also foresee, or do you have examples of medical applications that require other large data sets or other types of collaborating between the systems and persons?
Certainly, all that physiological modeling, for example, that's all data-based. I mean, that's that all the imaging that I've talked about in terms of they may use video as a way of transporting it, but I mean it's all bits as it starts off in terms of scan images. But take the physiological models. You've got very large physiological models, and you want to add some, let's say, pharmacological models to it as well. So you're talking about data sets where you're starting to build. I mean, if you use the sort of term web services interfaces among these various models, so that the physiological information is informed by the pharmacological information, which leads to some kind of treatment decisions in terms of what are the sort of approved approaches to a particular injury. And these are just sort of big data, first modeling and then data mining challenges. And the kind of data sets we're talking about, when you start talking about things down at the protein level, for example, are huge, gigabyte, terabyte, petabyte size of data sets. And they don't all have to be moved in real time, but you want to be able to have them interacting with each other appropriately. And that gets back to some of the metadata standards for doing that.
Okay, thanks very much, Ted. I'd like to call a halt there. Ted, in fact, is chairing a session later on in the week and will be around, so if there are any other questions, Ted will be around. So thanks very much, Ted. Our next speaker, who's also talking on a medical theme, is Martin Beck from UNIC in the Netherlands, who's been with... all right, from UNIC in Denmark, I'm sorry. All right, I don't know how to recover from that, Martin. But one of the things that Martin has been with UNIC in Denmark for the last 20 years or so, and he's also well known in the Torina circles. If people have been at Torina conferences for the last few years, you'll see that the person that chronicles the conference photographically, and he's even proving it now, is Martin. And I commend anyone after the talk to go and look at Martin's photographs of both this and previous conferences.
Yeah. Let's have a smile. Well, thank you. Well, first I'd like to thank the program committee for being able to come on short notice, but this is really a topic that develops fast. Well, as an NREN, we are in the business of providing network infrastructure, but we're also providing usually other stuff, like, for instance, supercomputing facilities. Some of us are involved in that, or providing special things for physicists or the bioinformatics people, for radio astronomers and so on. We do that heavily. Then, a few years ago, we were at UNIC led to think about what are we really for healthcare. Is that important to us? Health research, is that important to us? Yes, it is, but what are we providing to those guys? Nothing really. Look at this. If basic internet connectivity, of course we provide that to hospitals, especially if it's a university hospital, no problem, we provide basic internet connectivity. But what about all the other nice stuff? Video conferencing, are they using video conferencing in hospitals? Yes, indeed, of course they are. We just saw several examples. But are we providing it? No, we aren't, because the usual video conferencing facility used by or provided by the NRENs cannot be used because of privacy constraints and so on. And also collaboration tools, we provide that, yes, but not to hospitals, to the health sector, and so on. IPv6 we don't provide to anyone. But apart from that, roaming services, security, grid and the like, we provide that but not to the healthcare sector. So simply, plain old internet is not just enough for them because of security constraints. And this is not only, I mean, securing the data while it flows on the open network is no problem, really. The biggest concern, if you want to provide internet connectivity or really serve the healthcare sector's need of IP traffic, then the biggest concern is actually that they need to open their firewalls to use the common network. And that creates a lot of holes in the firewall that no one really, that's very difficult to keep track of. And that's why they are really reluctant to do that. They'll much rather do point-to-point or closed networks or whatever. So you will see everyone in that sector too wants to exchange data, but they have firewalls, control mechanisms, so on, that prevents them from doing that, and they just can't open at the rate and at the number of connections that really is the need of the users in the health care sector. So we came up with a solution, the so-called connection agreement system. That is a little invention I'd like to tell about really here. First, if we look at the situation as it is classically, without the connection agreement system, usually we have a user at a hospital at the right, no, the left for you, and he wants to access a service, say a repository of X-ray images or whatever, at another hospital. Now, in order to do that, he has to identify, first of all, his local firewall administrator. That's the happy face up there in blue. And for a large hospital, that will be quite a challenge. Who of the maybe 3-4 firewalls at my hospital, which firewall is actually blocking my way to those data? And who is administrating it? That's, at least in my country, that seems to be a bit of a problem if you have a large hospital. Go down, ask if you ever get into a hospital, I hope you do for work, not for other purposes, but if you do, try to ask some doctor who is the administrator of the firewall that you are using. He doesn't know. Okay, so next thing. He has to contact, usually he knows who's in charge of the service, the repository, say, of X-ray images, but he doesn't know who is actually managing his firewall. And then they have to make some kind of agreement, either VPN or have a special connection or whatever, in order to actually supply the user over there with a connection to the service he wants. Now, and it even gets worse. Once the service, for instance, expires, it is shut down or whatever, who is remembering to remove the rules in the firewall rule set? I mean, it's not impossible to document, but it's not common in the trade of firewall administrators to document who ordered every rule and when is it going to expire and why do we have this particular rule in the firewall. It's just not there in practice. For a manual example like this, it's no problem, but imagine if you have a health sector of, say, just like here, 50 entities, and you want to make VPN connections between all of them or other kinds of connections, dedicated lines or whatever, MPLS networks. You get an amount of rules that are unmanageable. And that's why we came up with an idea called the connection agreement system, where you, instead of the words, I can show it in this picture. The local user, the user A down there, he doesn't need to know anything about who is his firewall administrator or the network topology or anything. He just goes to the orange box up there called the connection agreement system. There he finds in a repository all the services that are offered on this network. He finds it and he says, I want to connect to this one. Okay, so then a message goes out to both the firewall administrators and to the owner of the service. Do you want to accept this connection? And they all in this, they get a mail of course, and then they log into the connection agreement system and say yes, both parts of this, they accept this agreement, and then the rules in the firewalls are automatically updated if the firewall administrators allow it, Otherwise, they can review it first and then have it updated later on. Okay? Yeah, that's what it says there. I can show it to you. These are screenshots from our connection agreement system. It says here I have 2 agreements awaiting approval, which in this, yeah, we'll learn to spell it. Here we have it. The parts in white are just the audit trail of this particular, don't matter that. It's the part in gray that is interesting. It says who is asking me to have this agreement and so on, and I'll just approve it, and then the firewall rules are updated, and you can see the results afterwards. These are just of the several thousand agreements made in this way from our central connection agreement system. Well, in Denmark, this started in 2001, where some guys called from an agency called Medcom, which is a standardizations body for all of Danish healthcare. It's not a ministry of anything. It's a kind of association of all parties involved in Danish healthcare. They came to us and said, we want some kind of interconnect. You are running the Danish Internet Exchange. Why can't you do something like this? And we said, well, this is completely different, but we'll do it anyhow. And there was a tender, and we had a long process where all the political issues of this thing, of course, was dealt with. And then we went into regular operation a year ago. And let's have a look at the situation. You see the blurry thing up there is Denmark, and the blue lines are an approximation of the fibers that make out the Danish research network. Okay, so these are the fibers. And back in the old days, before we had this Danish healthcare network, if, for instance, the university, the hospital at the University of Odense in the middle of the picture wanted to exchange X-ray images with the University of Aarhus, for instance, they had to make some kind, the red one, some kind of special, actually they had a fiber connection. They could have anything, but not on the regular network, because it's people's chests and whatever they are transmitting. It's not allowed by Danish law. So they had to do something special, and the traffic was not running in our blue fibers. Too bad. Now, so we made this connection agreement system and set up a whole a bunch of, these are all the parties of the Danish medical, the Danish health sector, and today we have all hospitals on, we have all pharmacists, we have 1/3 of all general practitioners, doctors, we have the half of all the special doctors, and we have laboratories and all the local authorities and so on. So virtually it's everyone in Denmark who's now connected on this network, and well, we have some technical stuff. I'll skip that. But the thing is now, with the connection agreement system, it all runs on the research network in a VPN from, again, the traffic from the University of Odense to a central hub in Lyngby, and then that's up there, our main operational center, and then to Aarhus. So we've gotten the same traffic to flow on our research network, and everybody's happy. Now, this network, what is it used for? First of all, a lot of hospital equipment actually has a web interface. But if you want to sit at a GP and see, for instance, the scanned images of your patients that reside, but the scanned images are residing in a hospital, you have to have some kind of web access. So it is really much used for that. It is used for also various kinds of telemedicine. Even though Denmark is a small country, we have a lot of small islands, and to go into a doctor of those islands, instead of having to take the ferry, you just go to your local doctor, and then he calls on the video phone whoever he needs to consult along with the patient. Again, video conferences, of course, they use that. We also have a collaboration platform if, for instance, two doctors or so want to share information about a patient. where they don't share a common administrative system. They can upload the data into this collaboration platform and thereby look at it. It is also very much used if people are traveling across the border to get treated. Otherwise, we can't exchange the data, especially with German, they have a very rigid law on that. And also we have a national health portal, so that everyone who is in a patient record system in Denmark, they can access their own data through this national health portal. And again, the connection from this health portal to the real data is on this Danish healthcare network. Now, the direct benefits for the health sector is clear. Apart from what I've said, actually, a lot of e-prescriptions and other stuff like reimbursements, referrals, discharge letters and so on, they are actually small messages on the network that are exchanged. And they were exchanged for like 30 cents before we got this network. And then when we got the network, the price of those messages dropped by a factor 10. So that alone paid for the whole network. But you can't do that in other countries because you don't have that much message, that big a message passing volume. So this is a special case for Denmark, Norway, and Sweden, Finland, where you have that. Okay, but apart from that, we can see that the rise of use of online applications, online collaboration is really rising tremendously, and also we've got a more efficient market for service providers. Like, for instance, in the old days, if Agfa or Philips or Siemens, they had to make a service contract for some kind of X-ray scanner or MR scanner or whatever, they had to have a special line installed in order to log into the thing. Now they can just get one connection into the healthcare network, and they can make a connection agreement with whoever they want to sign a contract with. And that has given a much more efficient competition. So there's a lot of business case stuff in this. Now, this idea of a connection agreement, it has shown to work on different network architectures. We have all the traffic pass a central hub in Denmark, but in Sweden, as you can see in this one, where well, you have to interpret it, this black stuff is network traffic, network connections, whereas the red lines sort of symbolize that the proliferation or the distribution of rules, okay, into the little boxes that are firewalls. So I'll give you a moment to study it. But the idea is that we have the Danish hub. This is actually, all this is something that exists today, okay? So we have the Danish network, we have there's a Swedish network that is also connected to the Danish one. In Norway, they have connected various hospitals, and also we have VPN connections to some hospitals in Estonia and Lithuania. And in Sweden, for instance, they have an open MPLS network, and then they have the security in the firewalls at the edges of that network, and there the connection agreement system is used to document all the rules that are in all of those firewalls. So, Sweden is on. Norway is starting a pilot project about how to make this system nationwide, and we also have shown that with in some EU E10 project called Baltic eHealth, we've had these Estonian and Lithuanian hospitals, and we've also had expressed interest from many countries, but so far we are very happy about this and haven't had time. But anyhow, I think this is important because it is a thing that will come upon you no matter what you do. Now, look here. If we have the healthcare network, then suddenly, okay, the healthcare network itself does not provide basic internet connectivity. We did that as an NREN, or any telco can do that really. It has nothing to do with this. But once we're in the network, we can again put a box on that network and provide video conferencing services, which we do. collaboration tools. I showed to you a screenshot there. Roaming services, grid security, whatever, is actually on that network. So we are now back in business, also for the healthcare sector. So have we solved all problems? Well, we've shown that you could create healthcare networks in quite an inexpensive way. I'll come to the figures in a moment. And also we have found a cheap and easy way to actually manage the increased complexity if everybody wants to make private connections to everybody, really. But it doesn't solve all problems, of course, because this is a system that provides network connectivity, but it does not ensure, for instance, that applications can talk to each other and so on. We don't do that. In Holland, for instance, they have a project that is focused on the application side, but not on the network side, so that's another approach, naturally. So what will it take to do this at home? The only thing you have to do is to team up with your local and friendly health authorities. Because if you do that, you can get the software for free. It is written using open source tools, and you can have it for free, but it is these Medcom guys that have paid us to do it. They have as a prerequisite that it is the health authorities they give it away to. And they have to sign a memorandum of understanding that any further developments will be given back to the community and so on and so on. And all you do is a few servers and routers to have it from a technical side, and then of course these 100,000 euros is what has been proposed in Norway and Sweden to actually have it in place, because you have to assess the network structure, you have to actually talk to a lot of firewall administrators and so on, so there's quite a lot of work in implementing this, but I mean it has been done in middle-sized countries like this for 100,000 euros. So again, and of course you have to have a team supporting this. So I think this is really an opportunity for the NRENs of Europe. Now, we have the skill and the attitude to do something new. This, I just explained, is too complicated really for a standard telco. If I tried to explain this to several telcos, and they two foils and they are lost. Now, I think you can understand this, you could build it, and that's why I think the NREN in most countries would be the ideal partner for the hospitals to have a network like this. And this is only, from an NREN perspective, I think this is not only a thing where you do something special for for a start, it's something special for the healthcare sector. But in a future to come, I can see that there is a rising need for private connections through the network. Private connections, not like lambdas. Of course, there's a need for lambdas, but I mean, governed by the end users, it would be nice to make just a VPN from end to end. I call them here ultra lightweight lambdas, and it has nothing to do with light waves or anything. It's just a point-to-point connection through the regular IP-based packet-based network, simply. But the idea that any user can do this tomorrow is quite fantastic. They find uses of it that you couldn't think of, and you keep their traffic in your network. And another thing is that I think the main growth in traffic will not happen on the open internet. The main growth in traffic, also the applications that Ted Hans shows us, for instance, they will have to be in somehow closed networks because of security issues. So get that traffic onto the network, and if you don't do it, someone else will, because this is a need to have all these entities we've created on the network guarded by their own little tiny firewall. All of these entities will sooner or later need to connect with close connections with private connections to each other, and you'll have to have some kind of broker in there. And if you don't do it, somewhere else, someone will establish this service. And they can do it even without asking you. I mean, we've established a connection to for instance, the hospitals of Lithuania, even without consulting the network there. We've just done it. Everyone can do this. They may be doing it right now without you knowing. Okay. So I propose a little bit of homework until the next time we see each other. You have to decide whether you want to provide such a facility for user-managed closed circuits in your network, or you would rather let someone else do it. Okay? And you also have to decide whether you need this growth in traffic and this, of course, growth in funding that such a facility will cause, because you can really charge a lot of, we charge, for instance, what is 10 cents per inhabitant in Denmark, simply for just having this network on. And the local authorities, they've accepted it because it really solves the problem for them. I think you can go home and do a similar thing. Think about that.
Okay, thanks very much. Thank you, Martin. There's obviously a challenge out there for the NRENs. Are there any questions?
Otherwise, we'll be here.
Okay. As I said, Martin, it's a challenge for the rest of them to catch up. So thank you very much indeed. And we have to do a bit of changing with the technology here. But our next speaker is Marco Berni, who actually changes the topic a little bit from very medical and scientific aspects to the arts and to the art side of our business. And it demonstrates that the requirements of the sciences are equally balanced by the requirements of the arts and archaeology and history. And I'll go across and try some. Right. Right.
Okay.
Marco works in the
History of Science Museum of Florence, and I work on the website and databases, and we at the museum we prepared and opened on this March. Thank you. An exhibition on Leonardo da Vinci, and this is the real exhibition is on the Uffizi, is a part of the Uffizi Gallery in this month until January, and but we prepared also a virtual exhibition which is on the web. And so I can try to make some confronts with the real and the virtual exhibition. So, okay, this I can skip this. The exhibition is on the genius of Leonardo, on the whole Leonardo, not because there are many exhibitions on Leonardo, but almost are focused on some specific area of his activity: art, anatomy, technologies, water, flight, and so on. This exhibition, The Mind of Leonardo, offers its visitors a different point of view and invites them to explore the genius, the mode of thinking, his conception of knowledge, and the laws that govern all of the operations of man and nature. So this approach gives rise to a different image, one that helps to dissolve the aura of mystery in which the myth of Leonardo has often been shrouded. A mind that tenaciously endeavoring to decipher the rational processes that animate the phenomena of the physical world, as well as the motion of thought, driven by the desire to achieve a perfect imitation of nature in drawing and painting. So this is a fly on the mountain. Here there are drawings, because it's inside the office, so there are original drawings. There are models, there are animations, there are virtual models, and so on, and manuscripts. So, for instance, this is a model rebuilt one-to-one scale of the Sforza monument, which was studied but never realized from Leonardo for many reasons. And so when you walk in the exhibition, you can understand how giant it was. And okay, so this is obviously just a part of the model, but beside it you can see the drawings from Leonardo for this model, the studies, or you can see the models here in the bottom. You can see the original, the drawings, the reproduction of the Leonardo drawings with didascalias, and there is a video, an animation, but it's burned, and in the photo, and there is from the original drawings on the right, you can see a model, multi-layer model, because this is the anatomy of the female body, and it's drawing like a multi-layer. And so in the model, each apparatus is shown on a different layer. So this is a section on the library of Leonardo. So he had many books. Here there are some of them he owned, and he designed instruments to draw and used instruments to draw. And here there are some reproduced in the exhibition. This is a view of the section on painting, showing explanatory models and multimedia illustrating physical concepts discussed in Leonardo's manuscripts. You see on the end two videos. There is a model showing some light effects on shadows and colored light. This is a model based on Leonardo's studies on perspective for application on frescoes on ceiling. If you stand from a particular point, you can see the drawing in the foreground, like if it was placed in the position of the drawing in the background. This is a perspective effect, and Leonardo studied it because if you have to make a fresco on the ceiling, and if you have a vault, you need to make some correction to the perspective in the drawing. And so this is many other models in the exhibition. So, and now we are at the virtual exhibition. We prepared it with the materials of the used in the real exhibition, and on the website are available all the exhibits, captions, models, and 3D simulations you can find in the real exhibition. So, before we can make some points on this, on the real and virtual, let's see some points of the exhibition. There is a section on scientific analysis of the adoration of the Magi. It's a study of Leonardo. And on this drawing there are some diagnostics investigations, and there are photos on visible light, infrared, and ultraviolet. And from each one you can, scholars developed some ideas about how he worked, what he drew, deleted, and so on. Here you can see an enlargement of a part, and here there are some points, some holes in the paper that were used to reproduce the drawing. So this is a sample from the Leonardo's writing desk, and because in the exhibition we tried to reproduce this, because he was a man that worked, he was a genius, but he worked normally. He read at the night with all the lamps, and so and this is there are some samples. You can see the draw quite old from Leonardo, but not the second. And you can see on the left a lamp from the original manuscript, and the reconstruction, the model that you can find in the exhibition, and you can find the photos of the model on the web. Then you can see some compasses for drawing, and ellipses, parabolas, cycloids. And these are models that are used to make obviously technical, but technical drawings and paintings. Okay, here there is a manuscript where it's illustrated the ellipsis construction, and we can try to show the animation which is on the web. It's on a TV in the exhibition, but it's also on the web, and we can try to look at it. Okay. Just to give you an idea of what. Okay, it's a loop. Okay, on the web we put a low quality version, but however, okay, let's see if it works this time. But okay, however, you can see the construction of the ellipses starting from a circle, and this is the method used in the drawing. Okay, we can stop it because okay, thank you. There are about 50 animations and of this kind on the web, and another point, the geometric man, the Vitruvian man, it's a mystery, but this is a mystery revealed because Leonardo studies the proportion of the human body and its commensurability with the perfect geometric forms, the circle and the square. This was a scientific analysis that had both cosmological meanings, the correspondence between micro and macrocosmos, and artistic ones, correctly representing the human figure and designing architecture based on the proportion of the human body. So, what's behind this drawing? You see two men, one in the circle and one in the square. The navel is the center of the circle, and the man in the circle is arm raised and legs apart. The man in the square is arms open and legs together. And okay, the side of the square and the radius of the circle represent the golden section. This is the golden section is a point very used in the Renaissance, and it's a proportion very used, very, very famous. And okay, this is there are many other proportions. So all the human body is studied as proportions. So the trunk is 1/4 of the height. The arm is 1/4 of the height too. Head is 1/8 of the height, and so on. Face is 1/10, hand is 1/10, foot is 1/7, and there are more. I don't bring here to don't bother you too much, but. Okay, so that's a mystery revealed because he wrote these proportions. Let's see another problem, another strong point. This is the Sforza monument, the equestrian monument to Francesco Sforza, on which Leonardo worked during his stay in Milan, was one of the most audacious artistic and technological challenges of the Renaissance. And Leonardo's approach depended on the study of the perfect proportions for the horse and on the definition of the muscular conformation of its pose. So he studied the proportions. He studied the technical problems for the molding of the statue. He could not realize it because Francesco Sforza was jailed from the enemy army, and but he lived as many studies, and here you can see some drawings and machines for extracting the mold sections, machine for transporting and turning the casting mold, a hoist, and here he studied the smelting system to put the bronze in the casting. And here there is a reconstruction from our multimedia laboratory, and we animated it, so I can try to show you. This is an animation. Okay. Do you think it's in the background? This one, yes. Okay. Okay. You can see the furnaces here. The liquid metal, because this was a very large project, and so it needed more than one furnace, so there was synchronization problems, there was many problems. He analyzed it. Okay. Okay, so let's see, give a look at what which typologies of material we offered in the virtual exhibition. We offered images like manuscripts, paintings, schemas, and rebuilt models, real and virtual. And there is a scientific analysis, there are animations, films, and tests. But why a virtual exhibition? Two main things: enrich the physical exhibition, to promote the real visit, to help prepare for the real visit, to document exhibition after its closing, and the other, extend services to a wider audience, to offer a virtual visit, to offer a permanent exhibition, to offer links to other applications, and to supply material for educational purposes. So, because on the the web, of the Museum of the History of Science, we have many other web applications which are in large part realized in the same situation. When the museum prepared an exhibition, a real exhibition, prepared a virtual exhibition too. So we have the Multimedia Museum Catalog, which contains all the objects on permanent exhibition, that are more than 1,000, and which have related resources like biographical data and in-depth information to give a contextual background for the selected objects, to explain scientific objects which are very difficult to understand for normal users. We have a virtual exhibition on Leonardo and the Engineers of the Renaissance, which was a former exhibition produced from the museum, which had many mountings in Paris, Florence, New York, London, and now is in China. And these are machines from Leonardo, from Brunelleschi, and the Chinese engineers. There is an application on scientific itineraries in Tuscany. This is not related to a real exhibition, but it's just a virtual exhibition to promote places of historical scientific interest in Tuscany. And there are other applications from exhibition, like the one on Pompeii, on Torricelli and the horror vacui, on the perspective, and so on. And all these applications, or the large part of them, are on the in a relational database, are stored in a relational database. We are moving all on the relational on the database because we find it's useful to manage information. So we realized an application which, starting from a word processor, put data, text, and information related to images and so on on a relational database, and from it we can manage it with an interface like Access, and we can generate a static and dynamic versions. For the web, we generate an XML format and transform it in HTML with an XSL transformation. And we used, for instance, for the multimedia catalog, the same application to generate an RTF file, which was used to produce the DVD of the collection of the museum. This gives us more flexibility because we have separated the graphics from data and are able to manage this separately. And so the next step, which we will start in the next days, is to integrate the whole. Because at the moment in our database, there are, for instance, 3 applications on Leonardo, totally disconnected, because there is the mind of Leonardo, which we have seen just now, mechanical marvels, the engineers of the Renaissance, and the car of Leonardo, which is another application. And so all of them are in the database. So we have to keep existing application to maintain a reference on the web to real exhibition. And we will add a virtual exhibition that gathers and integrates existing data, having at the same time a centralized system for data and applications. And we have the chance to share services with different applications, for instance, the digital library and LOPAC, carrying out a complete integration of all the archives of the museum. This is the opportunity for the creation of a network for the history of science to interchange information among community members. So we have to go out from our walls and to share our data with the community of the history of science. We can use this database to collect metadata from other applications, not necessarily contained in it, like the OPAC, the digital library, etc., to give the web users a unified interface. And to make this, we have to create, but we cannot do it alone. We have to create a network infrastructure for sharing information among the history of science community, allowing integrated access among distributed resources, and producing a semantic search system for resources. And this can be achieved by the creation of shared resource of web services, metadata, and search system. That's all. Thank you.
Okay.